So the limit of a function is what 2.2 covers, and there's a lot of different ways to look at a limit. But what the limit of a function really is the y value that a function approaches. That's what a limit is, a y value. And so when they look at a limit, we let x approach some value on the x-axis, and the y value of the function, if you're walking along the function, as you get so close to an x value, the limit of the function there is where it looks like the y value will be. And if you look, you can see the notation we use for this is the limit as x approaches a of f of x. This is the notation that we're using, and that notation means where does it look like the y value will be on the function, on the graph, when x gets close to the value a. And so here's some pictures that show you how to observe a limit on a graph. Keep in mind, when you're finding the limit from a graph, the limit is where it looks like the y value will end up. So if you imagine yourself walking along the graph towards the x value that we're asking about, from both sides, first you walk up towards that x value from the left and look and see where it looks like you're going to go, and then you walk from the right and look and see where you're going to go. And where it looks like you're going to go is what we call the limit, the y value it looks like will go in. So if we look at graph A here, graph A here is a graph of a function that has the limit as x approaches a of f of x is L. A and B both have this property. So the way to show that is to imagine yourself walking on the graph. So first I'm going to stand on the left-hand side of A. Now in a moment we're going to hear about standing on the left side is called the left-hand limit, because you're looking from the left. But if I was this little stick person and I looked down to see where I thought I was going to end up at when x was A, it looks like when x is A, the y value I'm going to end up at is going to be L. So the limit as x approaches A from the left-hand side is y equals L. Well, I also have to look at it from the other side. So I imagine that I'm another stick figure standing on the graph, but on the right-hand side. And again, I'm walking towards x equals A. So as I approach x equals A, walking on the function, I look down and see where do I think I'll end up when I get to x equals A. And the y value I see over here is, again, just like before, L. So the little red guy or girl standing on the left gives me a left-hand limit of L. The little blue stick figure standing on the right also gives me a limit of L. That's the right-hand limit. And both of those are exactly the same number. So we say, well, it doesn't matter which side we come from. If we walk towards x equals A on this graph, it looks like the y value is going to be L. That's why the limit is L. Example B is really the same thing, except it's slightly different because there's a hole at A. If you look here at x equals A, this is the point we're worried about in the limit. At x equals A, there is no y value. There's actually a big gaping hole there. And that's what that represents on the graph. But the limit, it doesn't matter what the actual y value is. If I wanted to know what the actual y value was, I would say, what is the y value at x equals A? The limit doesn't do that. The limit tells us where it looks like we'll end up when x is A, when we walk on the graph. So again, I'm going to stand to the left-hand side of this graph. This is the left-hand limit. And I want to see what y value it looks like I'm going to end up at when I actually walk all the way to x equals A. If I look there, it looks like the graph is going to be at the y value L. In reality, there is no y value. That's really a hole in real life. But it looks like I'll be at L if I keep walking. Now, I don't realize it, but when I get there, my foot is going to go through the hole. But I don't see it. All I'm doing is looking at the path. It appears I'm approaching L. So the left-hand limit, as x approaches A, is L, because that's the y value. Well, I'm going to look from the right-hand side, too. So here's the little blue stick figure. And they look down at where they think the graph will be when x finally reaches A. And again, there is no y value there. There's a hole. But this guy, when he looks, thinks he's going to end up at y value L. He doesn't notice. So the limit from the right-hand side is also L. So it doesn't matter which side you look from. When you walk towards A on the graph, it looks like you'll end up at the y value L, even though you'll fall through in reality. So both of these graphs, A and B, are examples of graphs where the limit as x approaches A of f of x equals L. Well, here's some examples of graphs where the limit doesn't exist. The limit doesn't exist if those two stick figures don't agree. If those two stick figures, the one on the left and the one on the right, think it's going to end up in a different spot, well, then we can't say that we know what the limit is, because it depends on what side you're on. It depends which one you are the left guy or the right guy. So if you look at this first graph, graph A, the actual y value is this top one, because that's where it's shaded. But if I draw a little figure to the left of x equals a, notice the limit as x approaches a of f of x does not exist in these examples. So these are examples where the limit of x approaches a of f of x doesn't even exist. If I was the right-hand person, and the left-hand person, and I looked at where I thought I'd end up when I got to A, it would be this little place, which I'll call Y1. The red Y1 is where the left-hand stick figure thinks they'll end up. If I draw a stick figure to the right of x equals a, notice all I'm doing is looking at x equals a. And I draw a stick figure to the left of it, on the graph, wherever the graph is, and I draw a stick figure to the right of it, on the graph, wherever the graph is. And the little stick figure to the right thinks the y value will be taller when he gets to x equals a. And we call that y2 in blue. Those are different y values. The left guy and the right guy think different things. So that limit doesn't exist because it depends on what side you're on. If you're the red guy is the left side limit. And that's really the limit as x approaches a, but I got to do something to let you know it's coming from the left. And what they do is they make a negative sign, a negative superscript, as x approaches a from the left. That's what that little negative sign right here says. The limit as x approaches a from the left of f of x. These will always exist, because you can stand on one side and look. But the limit the red guy thinks it's going to be is y1 in this example. I wrote y1 just to have a different number. The right side limit is the blue person. And the way we denote the right side limit is we write the limit as x approaches a with a positive superscript. And so what that literally says is the limit as x approaches a from the right of f of x. And we've noticed there above that we wrote y2 for that. Since y1 and y2, y1 and y2 are not equal to each other, the limit doesn't exist. And that's the exact same thing that's going on in graph B. If I stand to the right of, or to the left of A, it looks like I'm going to end up at y2. If I stand to the right of A, it looks like I'm going to end up at the blue spot, y1. And since the limits aren't the same, then we know that the limit does not exist. So in A and B here, the limit doesn't exist, because on the two sides it looks differently. And this is what we've already said. The one-sided limits are going to exist. The first one is the limit as x approaches a from the left of f of x. And that's how it's read. That's what the negative sign means. And the limit as x approaches a from the right of f of x. And what we use just there is, if we have a function f, the limit as x approaches a of f of x, that's the overall limit. That means it doesn't matter which side you look from, it's always the same. That limit exists if and only if the limits from both sides are exactly the same thing. And that's the fact that we used just a moment ago. If the limit from both sides is the same, if both little stick figures see the same y value, then that's the overall limit. We don't need the plus or minus on the a if it's the same from both sides. And so let's do an example where we can find some of these properties from a graph. Now here's a graph of g of x, and this is in the textbook actually. And in this graph, question A says find g of 2. Well, if you'll notice, the function's name is g of x. So if you want to find g of 2, you just plug in 2 for x. And what g of 2 means is the y value at 2. So I'm going to look here at 2, and if you look at x equals 2, there's two places where we have circles, but one of them's open and one of them's shaded. Well, the open one is a hole, The shaded one is the actual point. So at x equals 2, the y value is 3. So g of 2 is the number 3. Well, now we have to look at the limits. B here is asking us for the limit as x approaches 2 from the left-hand side. So I have to draw a little stick figure on the left-hand side of 2 and look and see what I think the y value will be. Even though it's not really the y value, there's a hole there. I think the y value is going to be 2 there. Because when I look at where I think the graph will end up, the road looks like it's going to stop at y equals 2. So the left-hand limit is going to be y equals 2. Part C says, find the limit of g of x as x approaches 2 from the right. So I'm going to have to draw a stick figure to the right of 2 on the graph. So here's x equals 2. I need to draw a stick figure just a little bit to the right, but on the graph. So that blue stick figure goes up here. And if the blue figure looks over at x equals 2, what he sees is y equals 3, is where it looks like he'll end up. So the limit as I approach 2 from the right is 3. Well, the last one says, what is the limit as x approaches 2 of g of x? And that limit doesn't exist because the left hand and the right hand side give us different numbers. So rewrite D and E a lot of the time, and that represents does not exist. It's shorthand. Well, then we get to look at x equals 3. So the first thing they ask me is g of 3. G of 3 is the y value when x equals 3. So if I go to x equals 3 and I look up the graph, there are 2 places where there are dots. That one's a hole, that one is shaded, so that's the actual y value. At x equals 3, y is 2. Now I have to look at the limits from the left and the right. F is, what is the limit as x approaches 3 from the left of g of x? So I have to go just a little bit to the left of 3 and stand on the graph. Now remember, I'm looking at 3 from the left-hand side, so I have to look over here. And the y value I think I'm going to get is y equals 3. So the limit as I approach 3 from the left is 3. Now the next one is, find the limit as I approach 3 from the right of g of x. So I look at 3 and I move a little bit to the right and stand on the graph. And I look over at 3 and I try to see what y value I think I'll get. And when I look over at 3, it looks like my y value will be 2. So the limit from the right of 3 looks like y equals 2. Well, the last one, H, says, what's the overall limit as x approaches 3? The left and the right-hand sides were different, so this one does not exist as well. So the last line is asking us to do the same thing at 4. So g of 4 is the y value when x equals 4. So when I look at x equals 4, the y value at x equals 4 is 3, because that's where the graph is. So at x equals 4, the y value turns out to be 3. Now j is the limit as I approach 4 from the left. So I have to draw a little stick figure to the left of 4 and look over and see what I think the y value will be. And when I look at x equals 4, it looks like the y value will be 3. So the limit from the left is 3. K is the limit from the right. So I have to draw a stick figure to the right of 4 and look over where I think I'll end up at when x is 4. It looks like y equals 3 as well. So the limit from the right is 3. Since the left-hand limit and the right-hand limit equal each other, the overall limit is that number. You don't need the plus or minus anymore. So that helps to give you an idea of how you can look at graphs to find limits. You're really looking at where it appears the graph is moving. Now the other way you can find limits is by using a table. And so if I want to find the limit, so that's what this thing is asking here. Find the limit as x approaches 2 of x squared minus 4 over x minus 2. And what that means is we want to see the number we get out when we use x values near 2. And you want to look at both sides. And then we can look at these numbers and see what they approach, or what this limit works out to be. So this top column is the x value that's smaller than 2. So these x values are going to be to the left of 2. And notice as I move along here, 1.9, 1.99, I'm getting closer and closer to 2. So what this does is it gives me a way to make a guess to what I think the limit as I approach 2 from the left will be. Because these numbers are smaller than 2. So I'm coming nearer to 2 from the left-hand side. And so I just take 1.9 and plug it in here for x. 1.9 squared minus 4 over 1.9 minus 2. And I pull out my trusty dusty calculator and I type it in. So this is the way I can figure out what the limit should be. And we're going to do the same thing on the other side. We're going to punch in numbers that are larger than 2 to approximate the limit to the right. So let's do this first one. We'll put in 1.9 squared minus 4 divided by 1.9 minus 2. When we type that in, we get 3.9 as the answer. Now we're going to put 1.99 in there. So 1.99 squared minus 4 over 1.99 minus 2. So you type that into your calculator. And you get 3.99. And now we're going to take 1.999 and plug it in there for x. 1.999 squared minus 4 divided by 1.999 minus 2 gives me 3.999. Just to be sure, we're going to try one more 9, so 1.9999 squared minus 4 over 1.9999 minus 2. And when you type that in, you get 3.9999. If you look at the pattern of these numbers, as I get closer to 2 from the left, it looks like that limit is approaching 4. Well, I'm going to do the same thing on the right-hand side of 2. I'm going to plug in numbers that are larger than 2, so it'll be on the right. But notice I'm getting closer and closer to the number 2 as I move along. 2.1, then 2.01 is a little bit closer than 2 because I have to move over. 2 is bigger than 1, so I have to get closer this way. So first I plug in 2.1, so I got 2.1 squared minus 4 over 2.1 minus 2. We type that into the calculator, and we get 4.1. We'll do the same thing with 2.01. That's a little bit closer to 2 from the right-hand side. So 2.01 squared minus 4 over 2.01 squared minus 2, or 2.01 minus 2. And you get 4.01. Put in 2.001. 2.001 squared minus 4 over 2.001 minus 2. Type that into your calculator, you get 4.001. Notice these numbers are getting smaller and smaller and closer to 4. And the last one, 2.0001 squared minus 4 over 2.0001 minus 2. And that gets you 4.0001 when you type it into your calculator. So if you look at the limit as x approaches 2 from the right, that looks like it's going to be 4 as well, if you look at the pattern of numbers. Since the limit is the same on both sides, we know the overall limit as x equals 4 is going to be that number, because we don't need the plus and minus on that 2 to describe anything. So that's the idea in 2.2 about being able to use limits along graphs and to use limits with tables to figure out values.